Okay, so what we are going to do is that we are going to start with the Fresnel and then Fraunhofer diffraction. This is the very core of this course. So let's start. The Fresnel and Fraunhofer approximation allows diffraction pattern calculations. So right now, what we can do is that we have seen those formula from Kirchhoff or Rayleigh-Sommerfeld integral form, but it is just a form. So what we need to do now is that how to calculate pattern calculation is very important. So we are going to start with the Fresnel approximation, and then we move on to the Fraunhofer approximation. And then examples of Fraunhofer diffraction patterns and the examples of Fresnel diffraction calculation will be given next week, okay? So let's start with some of the background. What we observe for the light, what we see from light is actually this case, power, optical power. Optical power is, if you look at it, its unit is watt, which means joule per second, okay? And it is proportional to, actually, is proportional to Poynting vector, actually. So what we actually observe is Poynting vector, and then it is proportional to field squared. Okay, so it is proportional to U squared. Okay, so eventually what we would like to do is that we want to find out U at the arbitrary point x, y, z for the given U, x, y, 0. And then from this, we want to calculate this, and from this, we want to calculate this, which is the pattern. So optical power is incident on the photosensitive region, leading to a photocurrent I that is response to the instant observed power. That the current is proportional to power times responsivity of our detector. And responsivity is proportional to these various numbers, like a quantum efficiency, eta QE. Q is the electronic charge, and nu is the optical frequency. Okay, so that is the current for photon energy. Okay. So how many currents are how much current we get for the photon energy or photon power? Okay, so usually if you look at it, it is the current is ampere, is power is watt. So responsivity is proportional to ampere over watt. Okay, that is usually the best definition of responsivity of a photodetector. And then in optics, the directly measurable quantity is optical power, or E square. And it is important to reach such power to the complex scalar field, UPT and UP. And let the medium be isotropic, and the wave is monochromatic. That means a single frequency. And then assuming the wave behaves locally as a transverse electromagnetic wave, then the electric field becomes this, very similar to plane wave. like this. And then power flows in the direction K, and the power density can be, as I said, is E squared, okay? And the total power incident on a surface area A, and then we get total power is the power density. So P is, if you look at it, is a dimensionless number. Is P is small p is the power density over area. So small p is power watt per area, and this unit is same as the Poynting vector. So intensity of a scalar monochromatic power wave at a point P is defined as the squared magnitude of the complex phasor presentation UP of this one. And then when a wave is not perfectly monochromatic, but is a narrow band, the intensity is given by this one. Here we are going to assume that U P T is given by U P T, okay? Monochromatic. Okay, so now assuming that, so what we'd like to know here is that we want to know U P0. This is what we want to know at this point. So this is the observation point. And we have this plane, observation plane. And then we have an aperture plane, aperture plane. And aperture plane and the observation plane is separated by Z. And then we assume that they are parallel. The parallel assumption is very important because we'll see later on, if it is not parallel, we have to choose different coordinate, and then it is very complicated. So for the time being, we are going to assume that the aperture plane and the observation plane are parallel to each other. And it is only separated by the distance Z. Okay, here is the case. The note that the coordinate we are using, okay, is that we have at the aperture plane, coordinate is C eta, okay? And the observation plane we have X, Y, and Z, okay? And we are going to assume that Z equal to 0 here, okay? So aperture plane, we have a certain aperture here. This is the aperture. And then the dark part is that simply the dark, there is no light. Only the aperture will transmit the light. That's the thing we need to know. So here is the case. P1 is on the aperture plane, and P0 is at the observation plane. Okay, P1 at the aperture, P0 at the observation point. This is the coordinate we are going to use. And the angle between P1 and P0 is given by theta, okay? And what we, according to Rayleigh-Sommerfeld or Huygens-Fresnel approximation, this is the relation between scalar field at the P naught and scalar field at the observation point, and I'm sorry, the aperture, is related by these equations. So note that there is some kind of spherical wave component along with the directional compensations, okay? Or directional weight. You may say that it is a weight. And then this is very simple, okay? So, but nevertheless, if you want to really calculate it, then it is a little bit complex. Before that, R01 is defined by the P0. Okay. And furthermore, this is just you don't have to derive everything, but you can just change the coordinate to the aperture plane, and R01 is given by z squared plus x minus c squared plus y minus eta squared. The reason why z is that we assume that z0 is 0, okay? And then there have been only two approximations in reaching this expression, this one. And the approximation inherent in the scalar theory and the assumption R01 is much, much larger than the wavelengths. And then this part becomes, becomes almost 1, okay? And then what we are going to do is that the R01, we take out z squared term out of the square root. And then we have a z, and then we have these terms, okay? And then we have only the first two terms. So if f is square root function, this can be approximated by, okay, so this is the Taylor expansion, nothing but the Taylor expansion. So we want to keep only the first term, okay? And then as I said before, R01 is very similar to Z. And then our approximation becomes like this. This is the UXY. Here, XY, UXY. This is what we want. And then this is given by U c eta on the c eta was on the aperture plane. Okay. And then this exponential, the spherical term, this term has been taken away. So remember that. So this was the z square R01 becomes Z plus something. So R01 square is the Z square. And then it goes like this, okay? So, so we have this exponential term, R01, R01. So we have a two approximation. This was taken out as Z square, okay? And then assuming that R01 is Z, but we cannot take this term because this is the phase term. So if you change a little bit, it could go to +1 to -1 rapidly. So we are taking this exponential term to the Taylor expansion. So there's two things. We have a R01 on the numerators and L01 in the denominators. The denominators is taken out of the integral because this is only integral for the sigma and Xi and eta, okay, over the sigma aperture. So R01 is similar to Z, then it is not dependent on Xi and eta. So we can just take it out. And then next thing is that R01 is Taylor expanded. And then we have these terms, okay? The Z term is taken out of the integral once again. And obviously Z over Z square becomes 1 over Z, right? Z over Z square becomes 1 over Z, okay? And the exponential was taken out of the integral. So now this is the very important form. Our scalar field at the observation point uxy is given by integral of our field at the aperture plane times this quadratic face, okay? But if you look at it more closely, then it looks like a kind of a convolution. Uxy times hx minus eta, y minus eta. So this is the convolution form, right? And convolution kernel is given by this one. We will see later on, this is the kind of a free space propagation. Free space propagation, impulse response, okay? But anyhow, we are getting close. We are getting close. And then another thing we would like to find out is there are two interpretations. One is the convolution. And another thing is that we just take out this form is x square and y square. Square, and then we just take out x square and y square once again because it is independent of a cos eta. We take out this term, and then we are changing form. Then we see that it is a kind of Fourier transform. This is the Fourier phase term, and then this is the function we want to have. So second interpretation is that our diffraction theory can be regarded as the Fourier transformation of the product of the complex field just to right to the aperture and the quadratic phase exponential. Okay, quadratic phase exponential. Okay. So either way, the equation 414 or 417 are referred to as the Fresnel diffraction integral. So this is the very important Fresnel diffraction integral. So let me just clear up. Okay, we'll go to that. This is the Fresnel integral, diffraction integral. This is the starting point of every conversation we are going to have. Okay. And Fresnel integral could be interpreted in two different ways. One is convolution or Fourier transformation. And there are some argument. I don't think it is necessary to go on. But what is important thing here is that okay, let's go to this case. Another interpretation we'd like to have is that how do we interpret Fresnel approximation in terms of angular spectrum? So by beginning with the equation 3.74, oh, I didn't, but you can look it up. You could look it up, your thing. And then this is this is shown in terms of this transfer function. I think that we had better separate the argument over angular spectrum, because the author of book is somehow just very briefly mentioning the angular spectrum method. And I think that we had better separate the angular spectrum and then make another lecture on this. This is so brief that, this part is just a formalism. But anyhow, according to the author, what he'd like to say is that in angular spectrum method, Fresnel approximation is nothing but by defining transfer function over diffraction as these two. So if our spatial frequency is given by this region, then we have a certain non-zero term, but outside is zero. Okay, this is the transfer function. And the Fourier transforming the Fresnel diffraction impulse response transfer function value for the Fresnel diffraction is given by this one. Okay. Note that this Gaussian, this is the kind of Gaussian with a certain factor. Gaussian becomes Gaussian, right? Fourier transformable Gaussian is Gaussian, right? So this is the things shown here, okay? So now let us try to think about some of the issues shown here. So you can, some arguments between the Fresnel diffraction between the confocal spherical surfaces and like this. Instead of a plane, they have some kind of confocal surfaces. In fact, this is widely used for the microscopy. So even though you have some kind of a corrections, but basically you're using lenses, and then you end up with this kind of a observation plane is not really plane. It is kind of a curvatured surface. And also in the case of aperture size, it's also kind of a spherical things. And then in that case, it's much more easier. And the Fresnel diffraction equation now becomes a Fourier transform of the field. So we'll see later on what we mean by we change the plane into a spherical plane is that we are using lens. Okay. So by proper lens, by proper lenses, we can change the scalar diffraction, Fresnel diffraction into Fourier transformation. Okay, so in other words, with the proper lens, then we can change the Fresnel diffraction into Fraunhofer diffractions. So we will see later on, but anyhow, it is important to note that Fresnel diffraction could be either convolution or Fourier transformation. So that's the two things you need to know. If you need to think about the convolution, then you need to points PSF or impulse response. And then from this, we have a transfer function, and et cetera, et cetera. And then Fourier transformation is just a Fourier transformation, okay? So now let us try to think about the next consequences. The most important approximation we have in the case of Fresnel diffraction was, so remember that this was the Huygens Fresnel expression, Fresnel principles integral. And in order to get to the Fresnel equations, we assume that R01 can be expressed as this one, okay? And then denominator becomes z square, and this space becomes this quadratic phase term. And then we get these equations. This was nothing but let's clear this up. This is the Fresnel, okay? This is very important integral, okay? Here we have assumed that R01 is z square, and then the phase term these are the two approximation. This is for the denominator, and this is the numerator. And then we further assume we are going to assume that Z is much larger than this squared factor coming out, okay? And then we just take out this term, and then we end up with this term. Remember that in the case here, once again, we have a x squared plus y squared, and then c squared plus eta squared, okay? And y eta. And then it is divided by all z. Okay, yeah. So what we are going to assume is that this term is nearly zero, okay? And this term is independent of a c eta we can take out, and then only this term is left over. Okay. And this term is nearly 1. And then we have this x squared plus y squared, and this term is 0, and this term is 1. And then we have this leftover term, okay, xc y eta term. And this is nothing but, if you look at it, the field at the aperture plane, and then this is nothing but Fourier transform phase factor, okay? So what is important thing is that we get Fourier transform. Fourier transform is our field. So Fraunhofer diffraction or far field is, we are going to assume that Z is much larger than this one. So if you look at it, this is nothing but the area of aperture. Area over aperture, K is 2 pi over lambda, okay. Area, okay. And then if that's the case, and then if the Z is far away, much far away from this value, then our field is nothing but Fourier transformation of the field at the aperture. But there is a very important step. So we would like to change to the Fourier transformation to special frequency fx and the special frequency fy. But remember that if we have a certain aperture on c eta plane, and then if we separate from this, then you have a xy. Okay, this is z. And if it's the z is large enough, aperture area, and then we note that it is Fourier transformation. U xy u c eta is related by the Fourier transformation. Okay, then it is a little bit strange. When you say we want to change to the Fourier transformation, that means the position becomes spatial frequency. In other words, xy becomes fx, fy, okay? But in reality, what we are actually observing is in real space. 자, 여러분한테 지금 헷갈리는 걸 얘기하는데 이거를 잘 생각을 해야 돼요. 자, 우리가 지금 수학적으로 아는 거는 파필드 패턴에서는 프라운호퍼 디프렉션이 일어나고 프라운호퍼 디프렉션이 따르면 스칼라 필드는 오브저베이션 플레인에서 스칼라 필드는 어퍼처 플레인에서의 필드를 프리에 트랜스폼 한 거다 이거죠. 그러면 이제 오케이 프리에 트랜스폼 했어. 그러면 약간 좀 이상하지 않나요? 좀 자, 스페셜 프리퀀시 스페이스가 어디 있죠? K 스페이스. K 스페이스가 도대체 뭔가? 여기는 포지션이니까 포지션, 리얼 스페이스니까 리얼 스페이스에서 프리 트랜스포메이션을 하면 레시프리컬 스페이스로 가잖아요. K 스페이스로 가죠. 스페셜 프리퀀시 스페이스로 간다는 얘기잖아요. 그럼 스페셜 프리퀀시가 어디 있죠? 여기에 있어야 될 거 아니에요. 여기에. 이 오브저베이션 플레인에 있을 거 아니에요. 그러면 이제 헷갈리는 거죠. 이거는 리얼 스페이스인데 여기에 나타나는 패턴은 프리 트랜스포메이션 된 거니까 이거는 스페셜 프리퀀시에 대한 함수로 나타내는데 이거 어떻게 된 거지? 그게 바로 여기에 나타나는 거예요. 자, 스페셜 프리퀀시 fx하고 fy는 이 지점에서 이 에퍼처 플레인에서의 fx, fy는 다른 게 아니라 여기 x도 y도 리얼 스페이스예요. 단 이거를 오버 람다 z라고 한 거예요. 결국 어떻게 되냐면 u, x, y는 이 비례하겠죠. 푸리에 트랜스포메이션 하는데 u, u 시에타 하는데 이밸류에이션을 할 때 어떻게 되냐면 이게 프리퀀시 함수로 나타날 거 아니에요. fx, fy로. 그러면 fx가 이거로 바뀐다는 거예요. 이게 굉장히 중요해요. 그러니까 이게 보통 수학적으로 말하면 그냥 물리적으로 생각하면 그래 양자역학적으로 생각하면 포지션 스페이스에서 모멘텀 스페이스로 바뀐다. 뭐 x에서 p 또는 x에서 k로 바뀐다 이렇게 생각할 수 있죠. 그건 당연하죠. 근데 그게 어딨냐는 거예요. K 스페이스가. K 스페이스는 사실은 우리 리얼 스페이스 안에 있는 거예요. 여기. 자, 그럼 여러분들 잘 생각해 보세요. 이제 여러분들이 이제 그 XRD라고 해서 엑스레이 디프렉션 할 때 엑스레이를 짜가지고 써가지고 엑스레이가 튕겨나가는 거 보고 엑스레이 패턴을 통해 가지고 거기서 나온 걸 모멘텀 스페이스를 해가지고 모멘텀 스페이스에서 나온 거를 프리 트랜스포먼 인버스 프리 트랜스포먼 시키면 샘플의 패턴이 나올 거 아니에요. 샘플의 스트럭처가 나오는 거죠. 자, 그렇게 통해서 우리가 DNA 스트럭처도 알아내고 다 알아냈는데 그러면 K 스페이스가 도대체 뭘까? 엑스레이를 디프렉션 맞고 튀어나간 거 아니에요. 튀어나갔을 때 디프렉션인데 디프렉션 된 스페이스 자체는 리얼 스페이스예요. 여기 X하고 Y는 포지션이죠. 포지션인데 근데 거기에서 나타날 때 프리 트랜스포메이션 되면 사실은 그 코디네이트가 X하고 Y가 오브저베이션 플랜에서 X, Y가 스페셜 프리퀀시하고 이렇게 리니어하게 연결되어 있다는 거예요. 자, 그래서 우리가 디프렉션 패턴 됐을 때 여기 어떤 XY에 여기 어떤 컴포넌트가 있고 여기 어떤 컴포넌트가 있다고 치죠. 그러면 여기 fx, fy가 여기 fx, fy보다 작잖아요. 그러니까 이거는 스페셜 프리퀀시가 작은 놈, 이거는 스페셜 프리퀀시가 큰 놈, 이렇게 얘기할 수가 있는 거예요. 자, 그래서 이걸 헷갈리면 안 돼요. 그러니까 리얼 스페이스하고 and reciprocal space. 또는 이게 R에서 K로 가는 거. 이게 사실은 또는 R에서 F로 가는 거. 이거를 연결되는 데가 바로 이거예요. fx는 x 오버 람다 z, fy는 y 오버 람다 z 이렇게 되는 거죠. 자, 이게 절묘하게 되는 게 GA도 관련이 돼 있고 X도 관련이 있고 또 웨이블랭스도 관련이 있는 거죠. 자, 이게 모든 정보가 다 관련돼 가지고 이렇게 되는데 디멘전으로 따지면 이게 원어블 랭스죠. 그러니까 스페셜 프리퀀시예요. 스페셜 프리퀀시. 시간 t에 대해서 1 오버 t가 되면 우리가 프리퀀시라고 하죠. 마찬가지로 우리가 이 포지션에 대해서 1 오버 L이 되면 이거는 스페셜 프리퀀시라고 얘기를 하는 거예요. 푸리에 도메인에서 푸리에 트랜스폼 할 때. 자, 이게 굉장히 중요한 컨셉트니까 여기서부터 헷갈리면 이제 리얼 스페이스는 어디고 K 스페이스는 어디냐, 나는 어디에 있냐, 이거 헷갈리면 절대로 안 됩니다. Okay, and then what we are going to do next is that the argument at optical frequencies, the condition required for the validity of the Fraunhofer approximation can be severe one. For example, if the wavelength is 0.6 micrometers in the red and aperture width over 2.5 centimeters, the observation distance Z must be longer than 1.6 kilometers. 자, 이게 어떻게 되냐 그러면 이제 이거를 만족하기 위해서 되는 게 이거예요, 이거. 이거를 만족하기 위해서 하는 거 보니까 G가 굉장히 큰 숫자가 나오는 거죠. 자, 그러면 이제 우리가 첫 번째 이제 페이퍼를 봤잖아요. 페이퍼, 저널 아티클. 거기서 보면 렌즈를 쓰는 게 나오죠. 렌즈를. 자, 렌즈를 써가지고 저 멀리 있는 것을 이미지를 우리가 원하는 위치, 포컬 랭스로 당기는 게 렌즈의 역할이죠. 자, 렌즈 역할은 다른 게 아니라 멀리 있는 상을 우리가 원하는 위치로 당겨오는 거예요. 그러니까 똑같은 방법으로 렌즈를 쓰면 우리가 푸리에 트랜스포메이션에서 저 멀리 있는 것이 포컬 랭스 쪽으로 딱 오게 됩니다. 자, 그래서 이제 푸리 옵틱스에서는 렌즈를 굉장히 많이 활용하게 됩니다. 아까도 얘기했지만 프라운호퍼 디프렉션 패턴이 먼데 있는 게 아니라 이렇게 아까 얘기한 대로 스페리컬 웨이브처럼 된다 그러면 converging toward the observer라는 얘기는 렌즈로 포컬 랭스를 맞춘다는 얘기잖아요. 그러니까 렌즈를 쓰면 똑같은 효과를 이룰 수 있다는 얘기입니다. 자, 그래서 오늘은 여기까지 하는 걸 할게요. 제가 여기서 딱 끊는 게 맞는 것 같아요. 그 다음에 이제 막 얘기하면 이제 굉장히 복잡해지는데 왜 그러냐면 이 얘기를 하고 나서 다음번에 했던 example 2를 쭉 하고 난 다음에는 바로 이제 매틀랩 애플리케이션이랑 같이 얘기를 할 거거든요. 그래서 이제 이 example 쪽에서는 매틀랩이랑 같이 이야기를 하도록 하겠습니다. 자.